of the streaming data. And let me first get started. And by introducing myself, my name is Matteo Merli, and I'm the CTO at Stream Native, and I'm one of the co-creator of Apache Pulsar, and I'm the PMC chair as well. And I'm also a PMC member of Apache Bookkeeper. And previously, I've been working at Splunk, Streamio, and Yahoo for several years, where we created Pulsar. So before introducing the data lifecycle, I just want to have like a different introduce the concept of the Pulsar and how it compares with data in motion. Typically, we have two different fields here. One is messaging, which is generally seen as message passing between different components, application, and services. And then we have streaming. And streaming instead is kind of like analyzing events that just happened. So it's kind of like, in one case, we have data that is being created. In the other, we are observing data, we're observing events that have happened, and then we are analyzing them. And the use cases typically are around like online transaction processing for messaging or integration across multiple systems. And the challenges are different than streaming. And the challenges for messages are generally like around the latency. People want to have low latency for messaging because most of the time there is a user waiting for that message to be published, because there is an action that will cause the message to be published. And availability. If this system is user-facing, it has to be highly available, and data has to be durable. If a user makes an action in the system, and that the message guarantees that the durability of that action, we cannot lose that message, because the user will lose his action. And more from an architectural perspective, messaging system typically will have higher level feature, things like complex routing, or like DLQ for retries, or like delays in messages, individual acknowledgements, out of order acknowledgements, and all these kind of features that are like more high level. And on the streaming side, we have systems that are more geared toward like real-time analytics. You have a stream of events that have happened, and you are seeing them and ingesting them, and then running a streaming analytic framework on top of it. And the main challenges for this kind of use cases are around throughput, because there is a lot of data. So like one user action may result in multiple services and microservices having taken actions, and each action is logged, and then it's collected. So there is an explosion there in terms of like through number of events and size of these events and so on. And typically, like analyzing these streams requires like ordering in the stream. You have like typically stateful processing that you're like accumulating these events into windows, and you need to process them in order by some property, by user, by group, and so on. And finally, the other challenge is that you have always the kind of like the real-time vision of it and the batch vision. So you have a stream of events, but you want to process also like the old events, and that is causing like more like a system problem in reading the old data. So when we say that Pulsar supports both this messaging and streaming, and how is that possible? The main thing is that Pulsar is based on a scalable log storage, which gives the durability, the scalability of and the very high throughput. But on top of this log abstraction, we have implemented flexible messaging semantics. So we use the log as the underlying storage, but we are applying layers that are implementing more high-level features on top of the log structure. And so the question is that, okay, why do we see that it's important to support both messaging and streaming? The thing is that messaging and streaming are applied. Like you can see that messaging and streaming are like processing data in different stages, but they're handling the same data. Like a user makes an action, then microservices will log some events, and then eventually the streaming will pick it up. The second aspect is that integrating messaging systems and streaming system, like when you have multiple systems in the loop, the integration between them becomes most of the time is like very complex. You have to reason about failures on each system and how they interact with each other. The integration point is typically very fragile because the availability is affected, the throughput, the performance consideration that happens when there is an outage in one of these two systems. And it is inefficient because you have to basically get the data into one system and then cascading into another system and so on. So when we see that we have this online processing world, and then we have the offline data services. So messaging is typically on the online side, and offline data services and streaming analytics is more on the offline, right? And Pulsar stands there, can support both kind of use cases. So just very quick, like high-level example here. So when we talk about online microservices, we have, for example, like we have a microservice A that takes HTTP requests from users, and this user request might be creating a user account. And to do that, the messaging will do it asynchronously. So it will publish a message on the messaging service. This message will get picked up by service B, which will run some kind of the logic. It might be multiple services picking up the same message and doing different actions there. At the end of the day, this will end up into a database, and that database may be used by service A to when it's serving user requests. The streaming analytics, though, is similar, but it's kind of like a different model here, right? So we have a messaging service that is used as the ingestion point. So you have the events that are coming from some source. You stage these events into messaging service, and then you run your stream processing framework on top of it. It can be Flink, Spark Streaming, or any other stream processing framework. And at the end of the day, you will get your result into some analytics database. The other aspect here that was not captured before is that there is always interaction bidirectional interaction between online and offline, in the sense that you have online services that are pushing a stream of events to be analyzed by stream compute framework, but you want to reuse the results of the stream compute framework and to drive the online services. For example, like you want that analytic database to be used to, like if you're using your stream compute framework to do machine learning and doing model, creating your models, you want to push those models back to the online to be used. And the interactions are complex. The question is typically that who is responsible for getting a feed of events? Where is the data is stored for this event? Is it on the messaging side or on the streaming side? And how can we circle back the updates back to the online messaging system? And what happens when there are unavailability? How can you ensure the schema, enforce the schema across all these systems that might have schema support, but they're completely separated, completely different models? And finally, what is the security model, right? You have one kind of system which is on security model and another one, and you have to match both the messaging and streaming system. So instead, like it becomes much more easier if you can just collapse everything into one single system. And in Pulsar, we support both. So that's kind of the main premise, that if you collapse both the online and the offline into a single system, you can basically have one copy of your data that is your online copy, but you also use that to drive the streaming data pipelines. But you also have a single system, a single failure mode, a single security model, and so on. And when you combine all that together, like the same example as before, like you can see that you still have your microservices, but the stream processing will be driven by the same topic that is being used by the microservices. And the result of that stream processing job will be written into an output topic. And that output topic is available to the online microservices so that they can read the results and update the serving the database. So basically, this becomes the full circle of the data, both on the online and the stream processing. The other thing is how to tackle integration points. So you have different kinds of services, but they can also share the same Pulsar cluster. Essentially, you are decoupling all these services using topics, and the topics will provide you the isolation across these services. They give you the availability so that you don't care about if service B is down, service A can keep producing on the topic. And the availability is given by the Pulsar system. So if you use Pulsar as a single data platform for all these kind of use cases, then you have a single tooling, a single way to look at your data. That supports many different APIs. Like we do have a messaging API, but we also have more like the data API, like batch API to do like more analytics on the topics and so on. Finally, there's a unified authentication and authorization, so you can decide which services have access to which data, and it's a single system to configure that. And finally, you also have the end-to-end schema validation. So since everything is in Pulsar topic, you can enforce the schema on those topics, both for online and offline. And finally, just a quick word around the data ownership here is that we only have one copy of the data because you can run your own data analytics directly on the data that was stored by the online services. So if you do have the event that is create a user, which is the event that has all the microservices that they have to do some actions to create this user account, the same event can be used by the stream compute job. So if you read the same exact topic, so you only have one single source of truth, you don't have data duplication there. And essentially, like you're also like removing who is the owner of that data, right? The data is not owned by one single component. Instead, you can just add access to any different consumer components to get access directly to the source. And finally, you don't need any additional ad hoc integration between system A and system B, or service A and service B, because they will all talk using the topics. So, like if you take the next step here, the next step here is that when you look at the data lifecycle, is that we can keep in Pulsar data for its entire life cycle. So from its inception, when microservices are generating the data, like generating the user account, they collaborate they exchange messages while they're creating that user account, for example. So that is the inception of the data. But then we have also the post-processing, the stream compute analytics that happens in there, and that also is driven by the Pulsar topic. But you can also extend that to more like a long-term storage. If you keep the data for longer time, then you can drive more like historical analytics on the data, or like either a stream compute job that will run from the beginning and rescan the topic data, but also like a more like batch, like access that is like doing segmented access on that data. So essentially, Pulsar can be the platform that supports the data from the very beginning to very long-term storage. So you only store it once, and it can stay there, and it is efficient in every single one of these stages. And if you're looking at the kind of like a time frame point of view here, so events are happening, so this is like really real time. When you're thinking about streaming analytics, typically like the latencies are it's still called real time, but it's really like a sub-second latency. You want to process the data very quickly, but there is not a user waiting for it. But you want to be as quick as possible to have that feedback loop of the stream compute results to be used in the online as fast as possible. And And then you have more like a data replay, which is typically like in hours or days, in which case you want to basically say roll back your stream compute position to the day before because you have a new version and you want to like reprocess the data. And finally, the long-term storage and batch processing, which can be days and months. And the way that we can support a month of data into the Pulsar cluster is typically using the tier storage feature, in which we can offload that tier of the cold data into S3 or DCS or similar cloud storage. For the facilities here in managing the data lifecycles are that one, as I said before, I'm reiterating here, but we only store the data once, and the data is available to all interested parties. So you can open that data feed to anyone, and using the ACLs and the authentication authorization, and we are able to hold the data for very long, extended amount of time. So essentially, what you get with Pulsar is an infinite stream storage abstraction, a stream storage that gives you low latency writes and isolation between a tail read and catch-up reads. Tail reads are like when consumers are caught up with the writers, and catch-up reads are when the consumers are like far behind. So if you roll back your consumer by 24 hours, then they're going to be reading from disk. So they're catching up with the producers. And also long-term tier storage. The other aspect in Pulsar is that everything was designed to be multi-tenant and multi-workloads. And that means that there has to be isolation across all these different topics and different producers and consumer, and isolation, and that isolation has to start with the I/O, so the access on disk. Otherwise, if someone is trying to write too fast, it will take out all the access to the disk, and that will impact other users. So we have really a sophisticated storage architecture in Bookkeeper that ensures that readers catch-up readers are not going to impact the writers, and that is the most important property to achieve isolation across different topics, across the different tenants and workloads. And also, like on top of the isolation, we have different kind of ways to limit the access to the resources. We have throttling per topic, per producer, per consumer, like all this kind of throttling, and we are also adding throttling per namespace or tenants, like kind of like with the resource groups concept that is coming into the .10 release, and quotas. So you have quotas, storage quota, so throttling quota, and so on. Now, if you put everything together there, like you can see, as Pulsar has the hub here as providing different kind of APIs, but it's a system where you can connect all your microservices, all your stream processing, and have all the interactions there. So on one side you have microservices, and this microservice can talk multiple protocols. So Pulsar protocol is the default it is one, but you can also, using protocol handlers, you can also use different protocols, and you can enable different ways to talk with the Pulsar service, like using MQTT or AMQP, and the Kafka protocol with KOP, for example. We also have different ways that we let the stream computing and batch data pipelines to consume the data. So, for example, like they might be using a reader to read online data, but they can also use kind of like a more like a batch API to get access directly to Bookkeeper and the data. And on the left side here, I'm putting tier storage because that's the building block to achieve this infinite stream abstraction that you can keep for days and months. And the other APIs that are completing the picture here are the functions API, so that you can do that part of that stream computing, stream processing directly in the Pulsar functions for the simple use cases, and also the Pulsar I/O. So Pulsar IO connectors, you can have pre-made sources and sinks that you can use that to get data in and out of the system. So to concluding this presentation, just want to leave with the thought that Pulsar, it is uniquely suited for its own architecture and the way that it is structured to be the data platform that powers all the data in motion use cases and all the interactions. So you can drive like every use case that has data in motion is typically a very good, is very well suited and supported by Pulsar to have interacting all the systems and all these components there, and both for like availability, performance, and security, and everything else. So I'm concluding here, and I'd be happy to answer any questions.